In the last video, we saw our first glimpse of differential equations. We saw that a differential equation is an equation with derivatives, and the solution for a differential equation is a function that satisfies the differential equation. We saw a few examples here, and once again, we shouldn't need to understand where these solutions come from. We should just understand that we have differential equations, equations that have derivatives. We have certain orders here that we talked about, and then the solution is a function without derivatives that satisfies the differential equation. In this video, we really want to understand the relationship between a differential equation and its solution much more deeply. So before we look at more examples, let's take a look at a couple more terms. In this table above, we have what are called general solutions to the differential equations. And we know that they're general solutions because of these arbitrary constants, these c values. When we are given an initial condition, along with the general solution to the differential equation, we can find what is called a specific solution that satisfies the differential equation, and this specific solution will not have the arbitrary constants. When we have a differential equation along with an initial condition, this has a special name. This is called an initial value problem. Initial value problems are very important problems in engineering, physics, chemistry, all sorts of areas of mathematics and science. And we'll abbreviate initial value problem with simply IVP. So that stands for an initial value problem. Once again, an initial value problem is a differential equation along with some initial condition, and that will allow us to find a specific solution that doesn't have these arbitrary constants in it. Let's look at one more important term, and then we'll work through some examples. When we have a differential equation that's the first derivative equal to just a function of y, this is called autonomous. So an autonomous differential equation, we have a first derivative, and it is equal only to a function of y. There's no x's here. So when we see this g of y, we can think of this as there's no x's. Take a look at this table here. We have an example of an autonomous differential equation. This first one, the derivative is just equal to an expression in terms of y. And we've written dy dx, we could write that as y prime as well. So we have y prime equals 2y. There are no x's, so we know that this is an autonomous differential equation. Let's look at some examples where we think of the relationship between a differential equation and its solution. For example 3, we have a first-order differential equation. It is not autonomous because we have an x here. So it's not autonomous, but it is first order. And we're given some initial condition. The initial condition is some value for the function y that we're looking for. The first thing that we want to do in this example is to show that this function here is a solution to the given differential equation. How do we show that a function is a solution to a differential equation? Let's talk about that in detail. So we have the differential equation, which is y prime minus x equals y plus 3. And we're claiming that the general solution for this differential equation is y equals c e to the x minus 4. Now think of this as just regular old functions that we're used to working with. We have a differential equation, which is an equation with derivatives, and we're claiming that this function satisfies the differential equation. How do we show that this satisfies the differential equation? Well, the first thing I want to do is to find the derivative here. I know that my differential equation involves derivatives, so I first want to find the derivative of the solution. So to find y prime here, I simply take the derivative of this expression with respect to x. So this is dy dx. It doesn't really matter which notation I use here. But the derivative, well, I have a constant c times e to the x. So c times the derivative of e to the x, the derivative of minus x is minus 1, and the derivative of 4 is 0. So using my solution, I took the derivative and I came up with this. I want to show that this derivative, along with this value for y, will satisfy the differential equation. So in order to do that, I'm going to consider the left-hand and the right-hand sides of the differential equation separately. So here's left-hand side of the differential equation, and I'm going to compare that with the right-hand side of the differential equation. I'm going to use this value for y, I'm going to use this value for y prime. I'll plug them into the differential equation separately into the left-hand and right-hand sides, and then ultimately we'll see that we get the same thing. So let's just focus on the left-hand side of the differential equation. We have y prime minus x. We just found y prime. Y prime is this expression here. So y prime is c e to the x minus 1. There's y prime. Now we subtract x. So here is the simplified form of the left-hand side of the differential equation. Let's take a look at the right-hand side. For the right-hand side, we have y plus 3. So we'll write down y plus 3. Now y is this expression here. This is our solution function, so we're going to use this expression for y. So we have c e to the x minus 4. That's y plus 3. If we simplify here, we get c e to the x minus 4 plus 3 is minus 1. Take a look. This expression matches this expression. They're the same thing. Because the left-hand and right-hand sides of the differential equation are equal, we know that this function is a solution for the differential equation. We just verified that this is the general solution to the differential equation. Because we have equality here, we know that the differential equation is satisfied by that solution. Now notice how I separately work through the left-hand side and the right-hand side. We don't want to just start with one side and set it equal to the other one right away and start working through and mixing up the two sides together. We want to separately work through the left-hand side and then the right-hand side, simplify both sides of the equation, and then ultimately see that they both result in the same thing. Let's go back and look at the problem statement. We just verified that this function is a solution to our given differential equation. And there's actually a second part to this problem. We want to find the particular solution to this initial value problem. We have an initial condition here that we'll bring in now, and we'll use this general solution along with the initial condition to find the specific or the particular solution to this initial value problem. So we solved part A. Let's take a look at part B. And I realize I called this example 2. This should be example 3A. So let's take a look at example 3B. We have the initial condition that y of 0 equals 2. This means that when x equals 0, the corresponding y value is 2. So if we look at the general solution, if we put in a 0 for x and then a 2 for y, the only variable left would be the c, and we could solve for c. That's exactly what we're going to do to find the specific solution here. Now, one other way that we could phrase this initial condition is to say that the solution passes through a certain point. We could say that the solution passes through the point x equals 0, y equals 2. So if we think of this point in the xy plane, we are going to find a solution of this form that will pass through this point. So here's how we do it. We take our general solution. It's y equals c e to the x minus 4. Everywhere we see an x, we plug in a 0, we replace the y with a 2, and then we solve for c. All right, so y is 2, x is 0. The only variable left now is the c. E to the 0 is 1, so we have c times 1 minus 0 minus 4. And then we can add 4 to both sides, solve for c. We get c equals 6. So if we use the value 6 for this arbitrary constant c, then the resulting function will pass through this point. It will satisfy the initial condition. So the particular solution, or the specific solution, is y equals c, which is now 6, e to the x minus 4. This satisfies the original differential equation, and this also satisfies the initial condition y of 0 equals 2. When we have a differential equation along with an initial condition, we can use the general solution to find a specific solution that satisfies both the differential equation and the initial condition. Let's use Desmos to try to understand this relationship between the specific solution and the general solution a little bit better. So let's start by graphing the general solution. we have y equals c times e to the x minus x minus 4. And we get a curve that looks like this. If we move the slider around, we'll see several different functions. And all of these functions that we're seeing right now are different solutions to the same differential equation. And we like to be able to graph the differential equation, but it turns out you can't really graph a differential equation in the normal sense that we think about it. If we try typing in here y prime minus x equals y plus 3, we don't get anything useful because we're trying to use the derivative here, and we can't just visualize that in the normal way that we think of. In a future section, we'll actually see how to visualize differential equations, but it's not quite the same as just drawing a picture like this. So we can't just plot a graph of the differential equation, but we can look at the graph of the solution. So all of these different functions here are valid solutions. And we want the solution that satisfies the initial condition y of 0 equals 2. That means when x equals 0, y equals 2. In other words, we want the specific solution that passes through that point, which is right about there. And take a look at that. We get c equals 6. That's exactly what we just solved. So if we write in the particular solution, we have y equals 6 e to the x minus 4. There we have it. That is the particular solution that satisfies the initial condition y of 0 equals 2. In other words, it passes through this point. So we get a general family of solutions from a differential equation. And if we're given an initial condition, we can find a specific solution that satisfies the differential equation and the initial condition. When we have a differential equation along with an initial condition, that's called an initial value problem. Let's take a look at example 4. We want to show that this function is a solution to this second-order differential equation. This might look vaguely familiar. This was actually one of the examples on the front page of the handout. We have the same differential equation, and notice that the solution given here is the general solution. For example 4, we don't have a general solution, we have a specific solution, but we'll still work through the steps to show that this specific solution satisfies the differential equation. I would actually encourage you to take some time for each one of these examples and to show that each of these different solutions satisfies the corresponding differential equation. It's good practice to understand the relationship between a differential equation and the solution. So for example 4, we have the differential equation y double prime plus 5t equals 4y prime minus 5y plus 9. And our proposed solution is y equals e to the 2t sine of t minus t plus 1. Our differential equation is second order, so we're going to first find y prime from our solution, and then we'll take another derivative to find y double prime, then we'll check the left-hand side and the right-hand side, substitute the appropriate values in from y and the first and second derivatives, and verify that the left-hand side and right-hand side are indeed equal using this solution. So first step, let's find y prime from our proposed solution. Y prime here is the derivative with respect to t. Taking derivatives of this first term requires the product rule because we have a product here. So we don't just want to write the derivative of e to the 2t times the derivative of sine. We need to use product rule. So we start with the derivative of e to the 2t. That requires chain rule. We do the derivative of e to the power times the derivative of the power, which is 2. So the derivative of e to the 2t is 2e to the 2t. So we have the derivative of the first function. Now we multiply by the second, no derivatives. And then we add the first function, no derivatives, times the derivative of the second, derivative of sine, cosine. Once again, we're using the product rule to take the derivative of what we were originally given. Then we have the derivative of minus t, which is minus 1. Derivative of 1 is 0. So here is our first derivative. That's what we'll put into the right-hand side of the differential equation for y prime. We still need to find the second derivative. So for y double prime, we take the derivative of y prime. We need to use the product rule for this. So we do the derivative of the first factor, that's 2 times the derivative of e to the 2t. That will be 4e to the 2t times the second function, sine, plus the first function, 2e to the 2t times the derivative of sine, cosine. So I just took the derivative of this first term using product rule. Now I'll take the derivative of the second term, again using product rule. So we take the derivative of e to the 2t, 2e to the t, times the second function, cosine, plus e to the 2t times the derivative of cosine, which is negative sine. Then the derivative of the negative 1 is just 0. So I used product rule twice to get both of these two derivatives. Now let's simplify this expression here. We can combine some similar terms. I have 4e to the 2t sine of t plus minus 1e to the 2t sine of t. So combining those together, I'll get 3e to the 2t sine of t. And then I have a 2e to the 2t cosine plus another 2e to the 2t cosine. Those are like terms. Combined to get 4e to the 2t cosine of t. This is my second derivative. So now that we've taken our original function and found the first and second derivatives, we will compare the left and right-hand sides of the differential equation. So for the left-hand side, I want to plug in my second derivative plus 5t. So I start just by writing the left-hand side, y double prime plus 5t. Now notice, I don't want to just write the whole differential equation and substitute both sides at once. If I substitute right away in for both sides, I'm already assuming that I have equality. I don't want to assume that I have equality before I've shown that it's actually true. So I'm going to work separately with the left side, then separately with the right side, and after I've simplified, then I'll show that they're actually equal. So working with the left side again, we have the second derivative plus 5t. The second derivative is what we found right here. So we plug that in for y double prime, 3e to the 2t sine of t plus 4e to the 2t cosine plus 5t. So once again, we have y double prime plus 5t. That's the left-hand side of the differential equation. Let's focus on the right-hand side now. So once again, I want to keep these two sides separate for now. So just focus on the right-hand side. It's 4y prime minus 5y plus 9. And 4y prime is 4 times this expression here. So this is going to get just a little messy. 4 times y prime, which is 2e to the 2t sine of t plus e to the 2t cosine of t minus 1. There's 4y prime minus 5 times y e to the 2t sine of t minus t plus 1 plus 9. So once again, here I have 4 times y prime minus 5 times y plus 9. That is the right-hand side of the differential equation. I want to expand everything out here and simplify as much as possible. So let's see. Distribute the 4. So I'll take 8 e to the 2t sine of t plus 4 e to the 2t cosine of t minus 4. And then distribute the 5 here. So we have minus 5 e to the 2t sine of t. Minus 5 times minus t is plus 5t. Minus 5 times plus 1 is minus 5 plus 9. Now, one more step to simplify, and then we'll see that this actually matches the left-hand side. So notice that we have 8 e to the 2t sine of t minus 5 e to the 2t sine of t. So I can write that as 3 e to the 2t sine of t. And I'll just put a little dash through these to mark that I've simplified those. And then we have the 4 e to the 2t cosine of t. So plus 4 e to the 2t cosine of t. And then we have plus 5t. So plus 5t. So we've taken care of that. And notice what's left. Minus 4, minus 5, plus 9, those all cancel out. So we're just left with this as our simplified expression. Now notice, this right-hand side simplified to exactly what the left-hand side is. We just verified that the left-hand and right-hand sides are indeed the same. So we have equality. We could write kind of a concluding statement here. We could say the left-hand and right-hand sides are equal. So the solution satisfies the differential equation. Since this is such an important concept, let's just recap what we've done here. We started out with a differential equation. Here it is. It's an equation with derivatives. And then we had what we were told is a solution, and we wanted to verify that this was actually a solution. The solution does not have derivatives in it. The solution is just a function, just y equals f of t, just the normal way that we think about functions. In order to verify that this solution satisfies the differential equation, we have to find the first and second derivatives. So we found those here. And then we look at the two different sides of the differential equation. Substitute the value for the second derivative. We get this expression here. And then we take the other side, substitute in for the second derivative and for y. And after a bunch of simplification, we got the same thing from the left-hand and right-hand sides of the differential equation. We worked separately with the two sides. We didn't first set them equal to each other and then move stuff around. We worked separately with the left-hand side and then the right-hand side, and we simplified to show that they were both equal to each other. Therefore, this solution is indeed a valid solution for the original differential equation. All right, take a second to step back from all the busy work of this problem and just look at the differential equation and compare that to this specific solution. How in the world do we take something like this, a differential equation, and just come up with a solution like this? And let's actually look at some of these other ones. How do we come up with these different functions that satisfy the differential equation? Well, the answer is it's a difficult problem. As we start learning about differential equations, it's an important perspective to understand that in general, solving a differential equation is not an easy problem. There is no systematic method that will always work to solve any given differential equation. And you can think of an analogy here between differential equations and integration techniques. When we talked about integration techniques, we said that solving integrals was an art. We had different techniques and we had to use trial and error to figure out which technique was the best. And sometimes we can have very simple integrals, like we had the integral of e to the x squared dx, which looks rather simple, but trying to find the antiderivative is just impossible in terms of elementary functions. So differential equations is kind of similar in that way. We can have these different differential equations, but the way to come up with the solution, well, different differential equations will have different techniques for coming up with a solution. So we'll learn one method later on called separation of variables. That will allow us to solve a differential equation like this first one, and even the second one with some little tricks. But we'll really not see many methods for solving differential equations. And as far as we're concerned, these differential equations here, we will not see how to solve. We'll save that for a future class.